This is section 9.2, day 2. We have indeterminate forms, infinity over infinity, infinity times 0, and infinity minus infinity. A version of L'Hopital's rule also applies to quotients that lead to the indeterminate form, infinity over infinity. If f of x and g of x both approach infinity as x approaches a, then the limit of the functions equal the limit of the derivatives, provided the latter limit exists. The a here, and in the indeterminate form 0 over 0, may itself be finite or infinite, and may be an endpoint of the interval I of theorem 5. Example 4. Working with indeterminate form infinity over infinity. Identify the indeterminate form and evaluate the limit using L'Hopital's rule. Support your answer graphically. We won't worry about that part. Let's look at the graph of secant of x. And secant is a reciprocal of cosine. So cosine starts at 1, and then by pi over 2, it's at 0. So it does this little bit. And then for secant, we take the reciprocal of that. In other words, we turn the graph upside down. So as secant approaches pi over 2, this is shooting up to infinity. So the secant of pi over 2 is actually infinity. Let's look at the graph of tangent. Tangent goes from negative pi over 2 to pi over 2, and it looks like this. And we also have asymptotes at pi over 2. Now that's shooting up to infinity also. So really we have 1 plus tangent of pi over 2. That's also, well, it's infinity plus 1. It's still infinity. We have the limit. Actually, we're doing L'Hopital's now. Limit as x approaches pi over 2 of secant x tangent x over secant squared x. And that is equal to the limit as x approaches pi over 2 of tangent of x over secant of x. That's equal to the limit as x approaches pi over 2 of sine of x over cosine of x over 1 over cosine of x. And now we can multiply the top and the bottom by cosine of x. We have limit as x approaches pi over 2 of sine of x, and that's equal to the sine of pi over 2, which is equal to 1. Working with indeterminate form infinity over infinity. Identify the indeterminate form and evaluate the limit using L'Hopital's rule. Let's look at the graph of natural log. The graph of natural log has the point 1, 0, and then shoots up to infinity. It shoots up very slowly, but it does go to infinity. The square root of x looks very similar, except we start at 0, 0, and then it progresses up to infinity as well. So when we take the natural log of infinity over 2 square root of infinity, that's equal to infinity over infinity, and that's an indeterminate form. Let's do L'Hopital's rule, and we get limit as x approaches infinity of 1 over x over 2 over 2 square root of x. Now those 2's are going to cancel out and leave 1, and we can multiply the top and the bottom by x squared of x to get rid of the complex fraction. We have limit as x approaches infinity of the x's will cancel, leaving square root of x, and then the square root of x's will cancel, leaving x. Well, this is equal to the limit as x approaches infinity of, we would have x to the 1/2 over x to the 1, and when you divide, you subtract the powers. That leaves 1 over the square root of x. Now when we plug infinity into the denominator, we get 1 over the square root of infinity, which goes to infinity, and so the answer is 0. Working with the indeterminate form infinity minus infinity. Find the limit as x approaches 1 of 1 over natural log of x minus 1 over x minus 1. If we plug the 1 into the functions, we get 1 over natural log of 1 minus 1 over 1 minus 1. That's equal to 1 over 0 minus 1 over 0. And if you approach 0, that's like having extremely small numbers. When you have not a large number, but a number divided by a really, really small one, that's infinity. So this is actually infinity minus infinity. Let's work this one by doing common denominator. We would multiply this one by x minus 1, and we'd multiply this one by the natural log of x. We have x minus 1 minus natural log of x over, we'd have x minus 1 natural log of x. So there's common denominator. Now let's do L'Hopital's. We have the limit as x approaches 1 of, let's see, we'd have 1. The derivative of minus 1 would be 0. And then the derivative of natural log of x would be 1 over x. Over first times the derivative of second, which would be 1 over x, plus the second, which is now natural log of x, times the derivative of the first, which would just be 1. Let's multiply everybody by x. When we do that, we get x minus 1 over, this will be x minus 1 and then plus x natural log of x. Well, now if we plugged 1 into this, we'd get 0 over, and we'd have 0 plus, plug 1 in there, the natural log of 1 is 0. So we would get 0 over 0, so we can do L'Hopital's again, because that's an indeterminate form. We have the limit as x approaches 1 of, on top we just have 1, over 1 plus first times derivative of second plus the second times derivative of the first. And that's equal to the limit as x approaches 1 of 1 over, we'd have 2 plus the natural log of 1. And actually we plugged 1 in, so I wouldn't write the limit. That wouldn't be there. That's equal to 1 over 2 plus 0, so the final answer is 1/2. Forms 1 to infinity, 0 to 0, and infinity to the 0. That's all indeterminate forms. Limits that lead to the indeterminate form can sometimes be handled by taking logarithms first. We use L'Hopital's rule to find the limit of the logarithm and then exponentiate to reveal the original function's behavior. So let's just get down to an example here, working with the indeterminate form 1 to the infinity. So if we plug infinity into this x, that's going to be 0. So we have 1 to the infinity. We're going to let f of x equal the function 1 plus 1 over x to the x. Then we can take the natural log of both sides. That's equal to, and when we take the natural log, we can bring that power down. We have x natural log of 1 plus 1 over x. Now, to get L'Hopital's rule, we have to have a function over a function. That's equal to the natural log of 1 plus 1 over x over 1 over x. Now, if we multiplied the top and the bottom by x's here, if we multiplied by x over x, these would cancel and we get right back to where we started. Now we take the limit of both sides. The limit as x approaches infinity of natural log of f of x is equal to the limit as x approaches infinity of the natural log of 1 plus 1 over x, then over 1 over x. We can do L'Hopital's rule now, and that's equal to the limit as x approaches infinity of 1 over 1 plus 1 over x over, and then the derivative of the inside is negative 1 over x squared. The derivative of 1 over x is negative 1 over x squared. Now these are going to cancel out, and we have the limit as x approaches infinity of 1 over 1 plus 1 over x. Now we can plug in infinity. We have 1 over 1, that's 1. When we plug infinity into 1 over infinity, that's actually equal to 0. Well, the answer is not 1. The limit as x approaches infinity of the natural log of f of x is equal to 1. And we can we can use both of these as the power of e. So we can write limit as x approaches infinity of e to the natural log of f of x is equal to e to the first. And now we have the limit as x approaches infinity of f of x, e to a natural log, those cancel out. We have The limit, just f of x here, is equal to e. So e is the answer, e to the first power. Working with indeterminate form infinity to the 0, we're going to let f of x equal to x to the 1 over x. Then we can take the natural log of both sides, and we can bring that power down to the front. So 1 over x natural log of x. Now we have the limit as x approaches infinity of natural log of f of x is equal to the limit as x approaches infinity of natural log of x over x. Here we can do L'Hopital's rule. We have limit as x approaches infinity of 1 over x, and then just over 1. And that's equal to 0. The answer, however, is not 0. We have the limit as x approaches infinity of the natural log of f of x is equal to 0. Limit as x approaches infinity of e to the natural log of f of x is equal to e to the 0. So the limit as x approaches infinity of f of x is equal to 1. That's the answer we're looking for. 4 graphs you should be able to visualize: tangent, inverse tangent, secant, and cosecant. Let's take a look at these 4 graphs. Let's start out with tangent. We have pi over 2 and negative pi over 2. Tangent is graphed between these two values, at least one period of it. Now pi over 4 is 1, negative pi over 4 is negative 1, and then we have asymptotes at both negative pi over 2 and pi over 2, and this is what the graph of tangent looks like. Now why would we want to know that? Well, in this chapter, if you're supposed to find the limit as x approaches pi over 2 of the tangent of x, that's equal to infinity. The next one is inverse tangent, and this is where we switch x and y. Up here we're going to have pi over 2, and down here we'll have negative pi over 2. So inverse tangent of 1 is pi over 4. Inverse tangent of negative 1 is negative pi over 4. And the graph looks like this, and it's going to level off to pi over 2. So the limit as x approaches infinity of inverse tangent of x is equal to pi over 2. Secant of x. Secant is the reciprocal of cosine. Cosine starts at 1, goes to 0, down to negative 1, back to 0, and up to 1. Now anywhere cosine is 0, secant is going to be undefined, so that's a vertical asymptote. And then we just turn cosine upside down to graph secant. Now what we want to know here is the limit as x approaches pi over 2 of secant of x is actually equal to infinity. This right here would be pi over 2. Then the last one you should be able to get is cosecant. That's the reciprocal of sine. Sine starts at 0, goes to 1, down to 0, negative 1, back to 0. And anywhere sine hits 0, cosecant will have a vertical asymptote, and then we turn the graphs upside down like that. And so we could say something like, well, the limit as x approaches pi of cosecant of x is equal to infinity. This one's shooting up to infinity, at least from the left-hand side.